ऑडियो कैप्चर हो रहा है. नाइस. Right, let me share my screen. uh, I'll do a recap of whatever we did last time because ऑडियो था नहीं, so most of like बहुत कोई देख नहीं पाए थे. And so this is 7.5. This was MLE that we did long ago, right? So we discussed what is the difference between capital XI, small xi, वगैरह वगैरह. The main thing, I mean, the main thing that we require is how to, find the MLEs. Just a sec, someone joined. Huh. So, how we find the MLEs is essentially pretty straightforward. We need to make the likelihood function, right? So, uh, likelihood function is always there. You construct this likelihood function, and whatever likelihood how do you get the likelihood function? Well, you multiply the densities or probabilities of observing the random sample. So what what is the density, या फिर what is the probability that x1 takes the particular value small x1 times f2 takes the particular value small x2, and you do that, you end up with a likelihood function. Most of the time this likelihood function that we do end up with, that is not very easy to differentiate. So what do? We just take a log and we come up with this log likelihood function, which is much easier to differentiate and everything, because the multiplication breaks down into summations, and then we can easily take the differentiation, and then we need to set it to 0, and ultimately what we get is the our MLE. So that is the basically the bread and butter of MLE. There is, in most of the sums you can do like this. There are a few sums where you need to uh, there are a few sums where uh, just straight up differentiation won't work. For instance, this was um, one of such questions where this was given कि f of x is e to the power theta minus x and find the MLE. Now here, if you find the likelihood function, you will get this. You will get this e to the power n theta minus summation xi. When you take the log, you will end up with this n theta minus summation xi. Now the thing is, if you differentiate this, you will get nothing, right? So we did this. If we differentiate and set it to 0, we get n minus 0 equals to 0, which is n equals to 0, which is absurd, right? So this is very, so just differentiating won't work, so you need to kind of think about it. So what we want to do, we want to maximize the likelihood, right? So in such cases, you can just plot the likelihood function, and this is how the likelihood function looked like. It was just a straight line, and we kind of have this was something that we had to look at, कि what is the constraint on x, and इससे पता चला था कि there is no unique MLE. There can be infinite, not infinite, there is no MLE, because this was a, so here we have strict inequality that x must be strictly greater than theta, and this was, let's say, the minimum of xi's. uh, what theta would you pick? So since this was a open interval, you can get very close to minimum of xi's, but I mean, there are infinitely many. You can get very close to xi, but the only thing is you should not be equals to xi. So that created a problem, and that basically, from there we kind of showed that there is no MLE. The next question was, how do you uh, make, like, how do you make the existence of MLE, or I mean, how do you ensure that MLE will exist? Well, for that we just need to put a uh, we just need to make this a weak inequality so that we can say that okay, the theta hat MLE is going to be your just minimum of xi's, and that would have worked. So this was pretty much all about MLE. Just a sec. Yeah. And there were a few more questions of the same flavor. There is again, see, form the likelihood function, differentiate, set it to 0, you'll get the answer. That was, I guess, in 7.5. 7.6, what did we do in 7.6? 7.6 was properties of MLE. 7.6 was properties of MLE, right? And we had this very important property which was invariance. Ki if beta hat MLE is the MLE for beta, some population parameter, then G of beta ka MLE would be G of beta hat MLE, right? So this is something that was very useful, uh, because this allowed us to circumvent lot of hard work. We could have just invoked this invariance property and prove lot of things. So here I gave an example, right? So if the MLE of mu is x bar, what would be the MLE of this thing right here? Mu to the power 6 by 39 divided by root over mu. So we don't have to form another likelihood function for this parameter. We can just replace mu by MLE of mu, which was x bar, and whatever this is the MLE of this, right? So that is how that was like the major thing that we did in 7.6. Here is an example. So we have this PDF. We need to find the MLE of e to the power minus 1 by theta, not theta, e to the power minus 1 by theta. So what did we do? We first found out the MLE of theta, right? Because doing that is easy. We came up with this likelihood function. We knew that this is your absolute error or absolute distance from something, and that is minimized. So this is, since this is minus, if we need to minimize this, so overall the expression would be maximized. So we knew that the median minimizes this. So we just said ki the MLE for theta hat would be the median. Therefore, the MLE for e to the power minus 1 by theta would be e to the power minus 1 by MLE of theta hat. And this was essentially the thing, that the most important thing. The other thing was we discussed consistency. How do you prove consistency? And how do you prove consistency? Proving consistency was thoda sa involved. You would basically or generally you would have to basically come up with this probability, beta hat minus beta is less than epsilon. You come up with this probability somehow, if you know the distribution of beta hat, and somehow you come up with an expression on the right hand side, and you what do? You take the limit as n tends to infinity, and most often than not, whatever, so if you take a limit here, you take a limit here, and most often than not, whatever this expression is goes to 0, goes to 1. If this is greater than epsilon, then it will go to 0. So most of the time, some of the times you do this. There was this one particular question where doing that was difficult, so you directly invoke the weak law of large numbers. Weak law of large numbers essentially says the mean of whatever distribution converges in probability to the mean of the population. And since and again this is something that this particular thing, something that we came across was that if Zn converges in probability to B, then any function g of Zn, which is differentiable and 1 I guess, that also converges in probability to g of B. So this is not trivial, this needs to be proved, and it is proved in DGROOT chapter 6 somewhere. We just use this property and we use that to say ki acha, according to the weak law of large numbers is xn, if xn bar converges into its mu, then 1 by xn bar will converge in probability to 1 by mu, and we found out that 1 by xn bar is just beta hat and 1 by mu was just beta. So we proved that beta hat MLE converges to beta, which was to be proved. So these are a few things, and yeah, so this was pretty much it all about 7.5, 7.6. Now we are going to do 7.7, which is sufficiency. So sufficient statistics. So okay, so first off, what is sufficient statistics? What is the theory behind it? Well, sufficiency basically means that sometimes we don't have the entire information about the sample, right? So for instance, so the thing that is given in our book, suppose there are two statisticians A and B, and A has complete information, has complete information about the sample, right? About the sample. So let's say both of them are doing some survey on let's say how much marks students in some particular class in some particular subject have got, right? So this statistician A knows, let's say the sample size is 10, suppose. Okay, so this guy knows that the first student got 10, the second student got 20, third student got let's say 50, and so on, last student got let's say 35, whatever. So A has complete information, and both of them want to estimate both of them want to estimate mu, right? So both of them want to estimate what is the average marks of the students. What is the average marks? That is what they both want to estimate. Now A has this complete information that the first student got this, second student got this, third student got this. Now B doesn't have this complete information, in the sense that B doesn't know which student has got how much. So the question is, what is the minimal? So the question is, what is the minimum amount of information B needs to make an estimate that is as good as A's estimate, right? So that is the question. Since A has complete information about this, then A can do a lot of things, right? A can do the MLE, and basically that is what A can do. A can find the MLE of this, maximum likelihood estimator, for this mu, and he is going to make a prediction or something. Now the thing is, B doesn't have this B doesn't have this entire information, and the question is, what is the minimum amount of information about the sample B needs to have in order to make an estimate that is as good as A's estimate, right? So that is the question, and the answer to that question is sufficient statistic. Sufficient statistic. So what is sufficient statistic? Sufficient statistic is just uh, in sometimes just a function of sample values, right? So it is just some function of sample values, and the thing is we know what is the estimator for mu, right? So we know that uh, mu hat is just summation of xi by n, right? This is something we know. If you want to estimate something about, if you want to estimate the population mean, what we do, we estimate it using the sample mean. That is what we do. Now the thing is, we know this. Now see, the fact that A has complete information says that ki A can compute this summation xi. But let's say A computed this summation xi, right? Let's say it turned out to be 120, and he shared that information with statistician B. So B also knows that summation of xi is 120. B doesn't know that first student got 10, second student got 20, third student got 50. B doesn't know that. B all the everything that B knows is just that ki if I sum all of the marks up, I'll get 120. Right? Now, if B knows that, then we can also come up with this, right? So we can say ki, okay, fine, I know what the summation xi is, I know what the sample size is, I can also make the prediction of 120 by 10, which is 12. I can make this prediction, and A will make the same prediction, right? So A will also kind of predict ki the mu hat is somewhere around this. A will also do the same thing. So the fact that A has complete information about the sample doesn't really make a difference, right? The fact that someone, the particularly first student got 10 and the second student got 20 doesn't really matter when we make inferences, right? So sometimes it just doesn't matter. So here the sufficient statistic was summation xi, and we are going to show this in a couple of examples. We are going to show that summation xi is a sufficient statistic for some given distribution with some given PDF. We are going to do this, but this is the uh, idea behind sufficient statistic, right? You don't need complete information about everything. You need sufficient information, and that sufficient information, using that sufficient information, you can make predictions or you can make estimates which are as good as if you had complete information. So this is the idea behind sufficient statistic. Now in uh, relation to this, there was a few theorems that was really important. I forgot the name. Factorization criterion, I guess. There was also something else. So okay, so let's take a look at this thing definition. Ki x1 to xn be a random sample from a distribution uh, with the parameter theta. Let t be a statistic. Suppose that for every theta and every possible value t of t, the joint conditional distribution of this depends only on t but not on theta. That is for each. Okay, so this is we need to kind of decode this. One second. Right. So what there is being said. Um, just a sec. So this is basically the definition for sufficient statistic. Now, what we just said, it is just the same thing, but in more formal terms, and yeah, so in more formal terms. Now, uh, they are saying that x1 to xn is a random sample. So x1, x2, it's a random sample. Random sample in the what does random sample means? It means then each of these are identically and independently distributed, and it is saying that all of them are drawn from a population with parameter theta, right? So all of them are drawn from some distribution D with parameter theta. This d of theta could be anything, normal, mu sigma square, Bernoulli p, whatever. It's just notation, d of theta, whatever. Now t is a statistic. Now what is a statistic? T is a statistic, that is, it is some function of x1 to xn, right? It is some function of the sample values, and given the, so it is some function of sample values given your theta. Okay, now this t obviously can take lots of values, right? Now if the, if this probability, right? So if this probability, okay, so it's not given theta, you can, we can just write it as this, because so t is just some function of sample values, right? So let's, for instance, here t was summation of xi, so it's just a function of sample values. You take all the sample values and you add them up, that is your t here. So it is just some function of random value. What it says next is that the probability that this t will take a particular value, this t will take, so the probability that t will take some particular value t given your population parameter theta, this, whatever this expression is, it is independent of theta. So it doesn't depend on theta at all. It is just p of t equals to t, right? So if this happens, now this doesn't happen all the time. So if this happens, there is no point in highlighting it. So if this happened, then t is a sufficient statistic. It is all that this definition is saying, and there are a few other ways to interpret it. It basically says that t and theta are independent, right? So this is this. Now this what does, so it basically said for each t, right? So for each value that my sufficient statistic can take, the conditional distribution of x1 to xn. What is the conditional distribution? Well, when t equals to t, I'm saying what, that r of x1, x2, so on till xn takes this particular value t, right, given theta. So what did I do? I just replaced t with the thing that I had assumed. Now when will this particular thing will take this particular value theta? When my sample values will take particular values, right? So let's say x1 took some value, x2 took some particular value, all of them took some particular value such that t was equals to t and theta, right? So for instance, let's say I have three values, let's say I have x1, x2 and x3, and my t is summation of x1 xi, that is what my t is, and let's say each one of them can take xi, can take either 0 or 1. Now what are the possible values my t can take? T can have 1 1 1 3, 1 0 0 1 1 0, which is 2. It can have 1 or it can have 0 as its possible values, right? So what is the probability that t will take this particular value 1 given theta? right? So theta is my some population parameter. Let's say they follow some distribution t with parameter theta. So it can take the t can take the value 1 when, let's say, x1 was equals to 1, x2 was equals to 0, x3 was equals to 0, and this, right? Or it can be when, let's say, x1 equals to 0, x2 equals to 0, x3 equals to 1, right? So given my t equals to 1, what are the possible values that my sufficient statistic can take? So we can translate whatever this is to this, and now this basically is the expression for joint distribution of, just a second. So this is basically joint distribution of xi's given t takes the particular value t and my population parameter theta. This is what basically the definition, the expression that we get from the definition boils down to. And if this entire thing is independent of, so let's say we are often going to get some expression for this, okay, and whatever expression that we get, if that expression is free of theta, if that expression is free of theta, theta doesn't show up anywhere, then my t is sufficient statistic. That is what this definition is saying. Now this was okay, fine. Now the other important thing that we must know is factorization criterion. What does this factorization criterion say? It basically says that if the likelihood function fn of x given theta can be factorized as follows, which is, I mean, if we can write f of x given theta as some u of x times v of r of x comma theta, then r of x is the sufficient statistic, is the sufficient statistic, right? So it basically says this. Now it has a proof. I would have discussed the proof because it kind of makes it easier to understand what is going on, but that is going to take some time and I'm not going to do it. If you guys do it and have a problem, you can let me know, then I can specially discuss the proof. But even if you don't, I mean, you should understand the proof, because once you understand the proof, you never really forget this key, or you never really get confused about this entire thing once you understand the proof. So understanding the proof is kind of nice, but you can also do without the proof. But I'll give you like the idea behind what happens if you can write it like this, right? So sufficient statistics said that if whatever this expression is, if this expression is free of theta, then what does that imply? That implies that the joint distribution of xi's is independent with theta, so it doesn't depend on theta. Now, oh, and by the way, this is an if and only if condition, right? So if this happens, then r of x is a sufficient statistic, whereas if you know that r of x is a sufficient statistic, then you can write the likelihood function as like this. So it works both ways. Now what I was saying ki if you, so this is kind of what we need to kind of show. Like if you do read the proof of this, what you would have to show, uh, if part, so it has two parts, if parts and only if part. So if part mein you have to show ki uh, if f of xn can be factorized as this, some function u of x times v of r of x comma theta, then r of x is sufficient statistic. Now what does it mean to say ki r of x is a sufficient statistic? It basically says that if you kind of assume ki r of x equals to t, because that is going to make the notation simpler. Now if you assume this, then when you evaluate this expression, when you evaluate the joint probability function or the joint probability distribution of x1 to xn given t equals to t, t equals to t on this, or r equals to some t, and theta equals and some given theta, whatever you get would be, you know, not an expression of theta. So if you calculate this probability, and how you would do it, you would basically apply the conditional probabilities, what do you say, definition ki x1 x2 this xn and t equals to t and theta divided by what are the possible values. So x1 x2 dot xn given t, right, and theta, given t and theta. No, it is basically, it is all such given theta, it is all such value of x such that some the t equals to t. This is what will come in the denominator. And since this is my likelihood function, right? So see, t is just a function of x1s to xn, right? So I can just remove t from here, and it notationally becomes cleaner. Nothing else is going on, and basically on the top I have my likelihood function that this happens, and in the denominator I have summation summation of basically all those x which belong to AT, such that, and you have this. Now what is this A belongs to AT? Basically, if all x's belongs to AT, then x1, then basically r of x, x1 x2 xn will be equals to t, right? So because we have this here, so we cannot sum up for all x's. We need to specifically sum up those cases where this function evaluates to t. Just a sec. Uh, right. So in the denominator you basically sum up those, you sum up for those x's such that this r of x evaluates to this particular value t. And since we have assumed that f of xn, fn of x can be uh, uh, it can be factored like this, we basically do it we have v of r comma theta, and here also we have summation of v of u of x or v of r comma theta. And since this is not a function of x, this entire thing can be taken out of the summation, and basically this and this cancels out. So ultimately what you are left with is just an expression of x, not theta. And you can show this the other way around too, ki if this is independent of theta, then you can factorize it as follows. And that is the basic idea behind the proof, which basically revolves around the fact that we need to show that whatever this expression is, it is independent of theta. And this will make our lives much easier, because yeah, it will just make our lives much easier. So this was kind of all the theory that there was behind sufficient statistics. I don't know, I don't think if there is any more theory. So we can, solve a few problems. So should we solve a few problems, or should we like go to chapter 8? Hello, am I not audible?
One or two problem.
Okay, ठीक है. We can discuss more than one or two also. कोई दिक्कत नहीं है. Okay, so before that, this is the factorization criterion, and it is basically what it says, right? Ki if x1 xn has a random sample, is a random sample, um, and with a given parameter space, as in this is all the values that theta can take belongs to this uh, omega set, and then this t is a sufficient statistic if and only if the likelihood function can be factored as follows, and they have given the proof. And this is precisely what I was saying, right? Ki whatever this expression is, we can evaluate it like this. Ki x takes the values x given theta, and t takes the particular value t given theta, and this is the numerator is just my likelihood function. The denominator is all such values of x. They have written as y, but doesn't really matter. It is all those values of x, such that if x takes those value, then t will be evaluated as small t, and then again we can factorize this as this, and basically everything cancels out, and what you are left with is just this, just the u's, not the v's, and therefore this is independent of theta. That is what they have shown. Right, and now they have this examples, and then they have summary. So there is nothing really else. So for instance, let's discuss this example. This is not too difficult, so there is no point in discussing it. Uh, Normal distribution is something that we can't discuss. So this is also something that ma'am discussed. So let's work it out once more. Right. So sufficient statistic for mean when sigma square is known for a normal distribution. Okay, just a sec. This is recording. Huh. So, so what is the sufficient statistic for mu when sigma square is, and this really is something that we should look after, ki sigma square is known or not. So when it is known, what is the sufficient statistic for mu? So we know that so let x1, x2, so on till xn be I all of them are IID normal, right? So follow IID normal with mean mu and sigma square variance, or in other words, this is a random sample. Then what is f of xi of x? Xi takes this particular, what is this? This is basically just the PDF of sigma root 2 pi e to the power minus 1 by 2 xi minus mu by sigma whole squared, right? So this is the so this is the this. So what is my likelihood function? My likelihood function is, so whenever we are asked to check if something is a sufficient, or if something is a sufficient statistic for something, what we essentially need to do is we need to invoke this factorization criterion. So we just need to calculate this likelihood function and see if we can factorize this as follows or not. If we can do this, then whatever this r of x is, this becomes a sufficient statistic. So we'll do just that. So what is the likelihood function that x1 takes this particular value x1, x2 takes this particular value x2, and so on, xn takes this particular value xn, given what is given, my mu is my parameter and sigma square is my parameter. So if you do that, it is just each of them individually. So this is multiplication, I running from 1 to n, and each of them individually multiplied with one another, right? So and if you do this, what you will get this n times, right? So that thing is multiplied n times, sigma 2 pi whole to the power n, and we are going to have e to the power sum of this, right? Index में जो भी रहेगा, all of them are going to get summed up. So I have minus half xi minus mu by sigma whole squared. Now I need to see, so basically I need to kind of try and factorize this as follows, but it is kind of hard. So generally you would be told that show that summation xi is the sufficient statistic. So most of the time you would know ki what do I need to show. So if I know this, right, so basically I'm trying to say this more from a problem solving point of view, that if you know ki summation xi is my sufficient statistic, now your objective should be ki how do I isolate this summation of xi. And when you can, so there are multiple levels of isolating it. So right, so for instance here it is not isolated at all. So what you do is you expand it out in this formula, then whatever is not a function of xi you take it out. So you ultimately try to come up with an expression which is solely a function of summation xi, and when you can't anymore, that is the point that you have reached your answer. And so that is precisely what we will do. So this entire thing is not a function of xi, so we'll just not touch it only. There is no point in doing anything with it. So this will just be as it is. In the exponent I can take minus 1 by 2 sigma square out, right? And then we'll be left with summation xi minus mu whole squared. And again, so this is 1 by sigma root 2 pi to the power n e to the power. So again, since this is, I can just okay, no, I cannot do anything right now, so let's just work with this, right? And now I can so I have my summation here, and now I can break this apart. So I have xi squared plus mu squared minus 2xi mu, right? This is what I have. Okay. So again sigma 2 pi, let's see what else can we do. So e to the power minus 1 by 2 sigma square, it is summation of xi square plus this is summation of mu square. Mu square is just a constant, so we'll get n mu square, and here we'll get minus 2 mu summation of xi, right? And okay, this is thoda sa confusing. So we needed to show that summation xi is the sufficient, wait, is summation, it should be, right? Just a sec. Oh, right. So let's just write everything else down. So n e to the power. So if I, okay, let's just write it. So this is 2 sigma square summation of xi square, then minus 1 by 2 sigma square n mu square plus mu by sigma square summation of xi, right? So I just open the brackets up, and now what did my factorization criterion said? Okay, I should have, or I can have, something which is solely a function of x, okay, and a function of my sufficient statistic along with my parameters. I mean, I cannot take this out. I mean, I cannot isolate this xi's further from theta on my parameters. So uh, here what is my parameter? Here my parameter is mu, not sigma square. I mean, it is a parameter, but that is not of interest to us because we know sigma square, right? So sigma square is known. So for us right now, it is just a number. So what are the xi's that I can isolate from mu? I will isolate that, right? So this is not a function of xi at all. This is a function of xi, and this is, so kuch bhi nahi hai. So I can collect all of them in one function. So I can have sigma 2 pi to the power n e to the power minus 1 by 2 sigma square summation xi squared. Let's take this common, plus 1 by 2 sigma square n mu square, and times e to the power mu by sigma square summation xi. Now we have essentially factored our likelihood function. So whatever this is, right? So whatever this is solely a okay, sorry, no, I cannot factor it like this. So let's say this is this. Just a sec. So I put this thing and this thing together, right? And now what is the thing that what is my sufficiency? Now what is basically the portion which I cannot isolate any further? So times e to the power this mu by sigma square summation of xi minus 1 by 2 sigma square n mu square. Now earlier what I was doing, earlier I was kind of taking this term and putting it along with this, but that is not allowed. Why? Because I'll say why in just a second. But right now notice that whatever this function is, this is purely a function of my sample values, right? This is purely a function of sample values and no parameter. Again, remember our parameter of interest in this case is mu. So we are not going to consider sigma square as a parameter because again sigma square is known. So when you know something, right? So let's say we know it to be 1 or 2. So it's not really a parameter here. We know what the value of this is. So whatever this is, it's purely a function of xi. So this will be our u of xi's, where x is basically, you know, x1 equals to x2, x2 equals to x2, like that. So this is my u of xi. And what is this? This is my some function which is a function of my xi's. It depends on summation of xi's, right? Because it depends on summation of xi's, and it depends on my parameter of interest, that is mu, right? So what I have done, what I have managed to do is I have managed to factor my likelihood ratio into two different components, such as one is purely a thing of function of my sample values, and the other is also a function of sample values and my parameter of interest. Now I cannot isolate this any further. I cannot isolate this summation xi square any further. Why? Because it is multiplied by mu, right? So I cannot take it out. And what I was doing earlier, I was kind of putting this expression, in u of x. Now why is that not allowed? Because this expression is a function of mu, right? So I cannot put that here. So u of x must be purely a function of just mu, just xi's. There should be no parameters involved in u of x. That is why whatever that I was doing was wrong. So this is my entire v and this is my u, and hence summation of xi's is a sufficient statistic for mu. Now let's say कि sigma square was unknown, right? So sigma square is unknown. Suppose just a sec. Oh, so if my sigma square is unknown, then how should I be able to factor this? I should be able to factor this as some function of x and some v, which is some sufficient statistic that I don't know, comma mu, comma sigma square. This should have been my thing. Now if I am claiming that t is my sufficient statistic for both mu and sigma square, then I should be able to do this. Now if you kind of look at it a few times or for a few minutes, you'll realize that there is no way to do it. There is no way to take this xi square out and isolate it from sigma square. So now everything is multiplied to everything. There is nothing to be done. So this entire thing, both of these components, this blue component and the pink component, will become will become v function, and u function would just be equals to 1. Again, then in that case, I have again factorized this. But what does that mean? It means that whatever this function is, this is a function of two things, right? Apart from mu and sigma, this is a function of summation xi squared and summation xi's, right? Times this u of x, which is just equals to 1, because there is nothing to isolate any further. So what does that mean? It means that if I want to estimate my mu and estimate sigma square, I need these two quantities. I need the xi, all of the the sample value squared and then summed up, and I also need my sample values to be summed up. I need these two things if I want to estimate my mu and sigma square. If my sigma square is unknown, if it is known, then well, this is the case. If it is unknown, then I need both of these, and this again makes sense, right? Because when we want to estimate this sigma hat, what do? So the sigma hat MLE is just sample mean, right? Sample standard deviation. It is just 1 by n summation xi minus x bar square. So again, if you break it down, it will again be basically this. So if you do it like this, if you break it in a plus b whole square ka formula, you will get this. So which again says that if I want to estimate my sigma hat MLE, I need this summation xi squared and summation xi. If I don't have either one of these, I won't be able to estimate my sigma hat, and that is something that I can say from here also. So this was one example that is from the example. So it is given. So you guys can go back as long or as many times as you want. Now here is a nice list of questions, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All of them basically says ki show that. So for instance, here we need to show that for a Bernoulli distribution with a parameter p, which is unknown, I need to show that this is my sufficient statistic. For a geometric distribution with a parameter p, where p is unknown, I need to show that this is my sufficient statistic. So let's do 1 or 2 or 3 from here. normal this is something that we just did, right? So example, they have said that mu is unknown, sigma square is known. Here they have said just the opposite thing. They have said that mu is known, variance is unknown. So this is something that you guys should try it yourself because we have already discussed it. We can take a look at this. The negative binomial distributors with parameter r and p, where r is known and p is unknown, we need to show that this is sufficient statistic. So let's do this. So we need to show that for a negative binomial distribution with parameters r, which is known, and p, which is unknown, the or t equals to summation of xi is sufficient statistic. This is what we need to show. So again, so it is pretty mechanical what to do. So solution, what is my, so let x1, x2 so on till xn be my random sample. Random sample with negative binomial with parameters n, r and p, right? So r, p and n. What was negative binomial distribution? It said that what was it? It said r successes. I forgot. Special distributions, negative binomial. Right, so yeah, so negative binomial was the probability that the number x of failures that can occur before the rth success. So how many times I fail before I get a success, before I get the rth success. Okay, so that PDF, I hope you guys remember this. I hope I remember this during exam, but I guess this is something that we'll get in the cheat sheet, so not an issue. Point being key, f of xi of given x given r comma p comma n was also there, right? Oh, no n. Okay, is r plus x minus 1. Yes, choose x. This is p to the power r, q to the power what? X. Q is just 1 minus p. So right. So if this is the case, then what is my likelihood function? So what is fn of x given rp? It is this thing. So r plus, okay, so I have this thing multiplied, right? So r plus x1 plus 1 by x1, not by x1 whole to the power p to the power r, 1 minus p to the power x1, again r plus x2 plus 1, x2 p to the power r 1 minus p to the power x2, and so on till r plus xn plus 1 xn p to the power r 1 minus p to the power xn, right? So I have this all of this multiplied together. So this is my multiplication of r plus xi's plus 1 by xi p to the power nr, right? You have this n times, and we have this xi times, right? So again, now see, just look at, so this is already kind of factored, right? So this portion right here, right? So what is my unknown? My unknown is r, right? And this is the thing that I cannot isolate from r. So this is p to the power nr 1 minus p to the power summation xi. I cannot have, sorry, r is known, p is unknown. So I cannot isolate 1 minus p whole to the power summation. So I cannot break this thing down further just to have it explicitly as a function of p and then as a function of xi. I cannot do that anymore. This is the best that I can do. So this is the entire thing, that so this expression I cannot isolate my parameter p with xi's anymore, and this is just a function of my sample values xi's, right? So this is also a function of r, which is a parameter, but that r is known, so we don't care about that. So we are left with these two things, and I can take this as my u of xi or u of x, and whatever this is v of, it is a function of what? It is a function of p, n and r is known, so no need to write them, and here we have summation xi. So I was able to factor it in this form. So summation xi is a sufficient statistic. So most of them are just this. There is nothing really difficult going on here. We'll just take one more example for illustrative purposes, and that should be good enough, because there is nothing else really, और कुछ नहीं हो रहा यहाँ. That is basically it. Let's take okay, what do you want me to take? Assume, okay, what is this? I haven't tried this. x1 xn forms a random sample from a distribution to the exponential family of distribution defined in exercise 23 of section 7.3. Okay, let's try to do this. 7.3. Okay, this is okay. No, this is too difficult. I mean, not difficult, but this is very ugly looking. I guess we could somehow show it, but I don't think this we should do right now. It will take too much time, first of all, to figure out. Anyway, let's take some other one. Gamma distribution. Okay, let's take gamma distribution. So for gamma distribution, we need to show that multiplication of all x's is my sufficient statistic. So gamma distribution show that this is is a sufficient statistic, but for that first of all I need to find the distribution function of gamma distribution. इसको तो बड़ा नहीं कर सकते क्या? Oh, this is not even the distribution function. Uh, huh. This is the PDF. Hey, this is the PDF. I don't know. This is the PDF that I am aware of. Whatever. Whew. So let's just write it out. So f of xi takes this particular value xi is 1 by gamma of gamma alpha x to the power alpha minus 1 Okay, something is wrong. Let's just refer to the book. I think उधर कुछ गलत not गलत but कुछ ऐसा दिया हुआ जो नहीं पता मेरे को. Gamma distribution was here. Anyway, so it is what gamma of alpha beta to the power alpha x to the power alpha minus 1 and e to the power minus beta x, e to the power minus beta x. So this is for all positive values. 0 for all the negative ones. So I need to show that product of xi's is the sufficient statistic. So let's just make the likelihood function, and okay, what is known and what is unknown, that is something we need to take a look at. So sufficient, we are doing 6, right? So beta is known and alpha is unknown. Okay, so beta is known, alpha is unknown, right? So what is f of xn given beta alpha? It is power alpha gamma of alpha x to the power x1 to the power alpha minus 1 e to the power minus beta x1 and so on till beta to the power alpha gamma to the power alpha xn to the power alpha minus 1 e to the power minus beta xn. Now let's see what we can isolate out. So I have these things. So beta to the power alpha by this alpha, this is to the power n, this is something that we are going to get, x, and here we have So this x1 is multiplied, so all of these xi's are multiplied with each other, right, and they have an index of alpha minus 1. So basically what I have here is multiplication of all of these xi's, right, whole to the power alpha minus 1. So this is what I have, and here we have minus beta summation of xi's. So this is what I have. Now I need to factor it. How? I need to factor it something which is purely a function of xi's. What function is that? This is that function, right? So this is purely a function of xi's. It is also a function of beta, but beta is known, right? Beta is known, so we don't have to worry about that. And what is a function of my unknown parameter and my sufficient statistic? This right here, right? So I cannot isolate summation xi anymore. So this is my v function with this right here given alpha, and this is just my u of x, which basically shows that whatever this is a sufficient statistic for alpha, right? So most of these questions are like this. There is nothing really else going on. There are a few, I guess these questions are a bit trickier. I have not tried these yet. I don't think I'll ever have the time to try 13, 14, 15, 16. But ultimately we would have to do the same thing, right? Ultimately we would have to do the same thing, and I guess now so this is a question which is pretty easy. It basically says that this I have tried. So this basically says that if whatever this PDF is, and this t can be computed. So this t is a function of sample value, and t prime is a different function of sample values, and they have a 1-1 relation between them. That means if I can if I know what the value of t is, I know what the value of t prime is, and if I know the value of t prime, I know the value of t. So that now what they have said is that they have said that prove that t prime is my sufficient statistic if t is my sufficient statistic, and if t is my sufficient statistic, then prove that t prime is a sufficient statistic. You won't really have to do anything, you just need to do this, right? So assume, so if t is sufficient, right, and if you know t, you know t prime, right? So if t is sufficient, then you can have this likelihood function, and you can factor it as follows, right? You can factor it as some function of x and some function of v, which is a function of t, which is my sufficient statistic, and my parameter theta. Now if I know the value of t, I know the value of t prime, right? So what I can do, I can write it okay, so it's better to do it this way. Suppose t is my sufficient statistic, and then you claim that t prime is sufficient. Now we need to prove this. Now we need to prove our claim. So if t prime is sufficient, then we should be able to factorize this as follows, right? But we can just replace this t prime. We can replace this t prime with some other function, with let's say g of t of theta. So let us assume that t is or t prime is just some function of t, where g is 1-1 function, which is they have said this, right? So there is a 1-1 function of t. So there is a 1-1 relationship between them. So I can just assume that to be any function g, and I can have this, which is basically u of x is basically v of this is then ultimately there is some, let's say, some different function v prime of t and theta, which basically shows that t is my sufficient statistic. Oh, okay. So, okay, just a sec. So, what we did essentially, we have kind of assuming that t prime is sufficient, we have proved that t is sufficient. So, this is something that we are claiming. We are claiming that t is sufficient, and we are assuming that t prime is sufficient. Sorry for the confusion. So, basically the point is ki if we assume that t prime is sufficient, then we can factorize it as follows, and since t prime and t has that relationship, I can replace this t prime with some g of t, and then ultimately this function will change, but whatever I'll get afterwards would be just a function of t and theta, which basically shows that I can factor my likelihood function as this, which implies that t is sufficient. So, assuming one, I have proved the other. Now we need to do the same thing other way around, and this is what you have to do in 13. So, 13 is pretty easy. Rest of the one I need to take a look at. So, now let's just take a 5-minute break, and then we'll start with chapter 8, or at least what I know. I don't know a lot. I mean, I haven't practiced or anything from chapter 8. I am lagging behind too. So, we'll take a look at the chapter 8, and if what Ruby said that 8.5 tak hi hua hai, then we could do some things. So, I'll just discuss what I know, and maybe tomorrow what we are going to, so tomorrow we can discuss a few questions from chapter 8 and then get into chapter 9 as much as we can, right? So, let's just finish chapter 8 this weekend. Hopefully we'll sometime by next week we'll finish chapter 9 too, because chapter 9 is not that big. Chapter 9 may we have to do a lot of questions, but chapter 9 by itself isn't very big. It is just two things, 9.1 and 9.2. The other we don't have, other things we don't have. So so let's just take a 5 or 10 minutes break, and then we'll start with chapter 8. Okay. Right. So that was all about sufficient statistics, and now we are doing sampling distribution. Right. So, what is basically sampling distribution? Sampling distribution is basically, it deals with, so we have done lots of distributions, right? So we have done gamma, binomial, normal, etc., etc. Sampling distribution is kind of again, it's kind of an extension of that, right? So basically what we have is some sample values, right? And some, I mean, we have some statistic, right, which is basically a function of sample values, and we try to derive their distribution. Okay, so that is what we do, and that is basically what sampling distribution is. So what is the distribution of sample statistic? So we are not trying to figure out what the distribution of the sample is. The distribution of the sample is just going to be what the distribution of the population is, and that is something that we assume already, right? So if we drawing our sample from a supposedly normal distribution, then the samples distribution is normal distribution. That is a different thing. What we are trying to say is we have our sample, and then from the sample values we have calculated some statistic. What is the distribution of that? So for instance, if I this thing which is my summation xi by n, right, which is my sample mean, this follows a normal so not this, actually this thing, right. So if I have my sample mean minus my population mean divided by the variance of the mean, which is sigma square, which is divided by the standard deviation, sorry, sigma by root n, which we can write it as this. Right. So whatever this is, if let's say if my sigma is known, if I know what my sigma is, then this follows a normal distribution with parameters 0 and 1, right. So notice we are not making any comments about how the sample is distributed, sample values as in x1, x2, that is how is that distributed. We are not talking about that. We are talking about how this statistic, this entire thing is distributed. So what I can do is I can collect different samples, right. I can collect different samples, and for different samples I'll get different values of x bar, and then for each of those x bar we calculate this. I multiply it by square root of n, I divide it by sigma, and I calculate what this is, and after that I am done. If I then plot it, I'll get a normally distributed thing, right, if my sigma is known, right. So sigma is known. Now if we have the same thing, right, if this happens, but I don't know my sigma, so what I do, I replace that with sample standard deviation, right. If I don't know my population standard deviation, what the next best thing that I can do, I can replace this sigma by some estimator for sigma, let's say that is my sample standard deviation, in which case I am going to have this, right. This will follow a t distribution with n minus 1 degrees of freedom, right. So right, and what is n? N is basically my sample size. So let's denote this with this, where this is unknown, right. So like this. Now what are we trying to do with the sampling distribution? It is pretty much similar with what we have done with any other distribution, right. So given any distribution, just a sec. Right. So let's say, so earlier what have we done? Earlier we have said like, okay, x is some distribution which follows some distribution with parameter theta, and the central question that we basically asked is that what is the probability that x is less than some particular value, or x lies between two values. These are the normal questions that we have asked given any random variable following any distribution. The other things that we have done, what is the expectation of this, what is the variance of this. With sampling distribution too, we kind of do the same thing. We kind of ask the same kind of questions. Ki, what is the probability that my sample mean is going to lie between, let's say, 10 and 20, right. So this is something which is and so what we are doing is we are doing the same thing in a different context. And so what is the context here? The context here is inference, right. We want to infer something about the population parameter. By the way, this is not x bar, this is mu, sorry, because x bar we know what x bar is. We collect the sample, we can calculate this x bar. This mu is something that we don't know. right? So we are trying to say something about the mu, things that we don't know. So we are kind of answering the same kind of questions. Ki what is the probability that mu lies between 10 and 20? But now there is some added context to it. Now I am inferring something about my true population parameter. Ki given that my sample mean was, let's say, 10, what is the probability that my true mean, my population mean, will lie in this particular interval of 10 to 20? And if I want to calculate this probability, I need to know what the distribution of mu is, right? So I need to know how is that kind of distributed, but I do not know how this is distributed. But what I do know is how is this distributed, this thing. So what I can do, I can transform that. So I can subtract my mu minus x bar, so I can transform this, wait just a sec. So I can transform it and I can convert it into this particular format, and this is something that we'll see right now. And whatever we get here, so after I multiply and divide with all the relevant things, right, here also I would have to multiply and divide by the same things, right? I know what this distribution is. So then I can calculate this particular value. Let's say this turned out to be 0.5 or whatever. And from there we can backtrack to say something about my original mu. So that is what sampling distribution is all about. Let's just take a look at the book. What else is there? Right. So I'll be just giving a brief overview because, as I keep saying, I don't have much. I have not studied this very much. So Bernoulli distribution, this is something that we know. Okay. Okay, this is okay. So this is all about Bernoulli distribution. I don't know why they have repeated this, but I guess we'll have to see. Anyway, this is not the part that I am very interested in. Oh, acha, I'm in chapter. Okay, that is why. Chapter 1, yes. So statistics and estimators. We already know what statistics is, and we already know what estimators is, right? And then we have sampling distribution. Suppose we have a random variable x from a random sample from a distribution involving a parameter theta. So this random sample is drawn from a population with parameter theta, and t is my statistic, a statistic or whatever you call it. It is it's a statistic, not whatever, it's a statistic. What is a statistic? Statistic is a function of sample values. So t be a function of t and possibly theta, and so we can write it like this, right? So it's a function of xi is x10 and theta. Now the distribution of t is known as the sampling distribution, which is precisely what I said, right? So I want to know the distribution of x bar, s square. These are all sample. These are all functions of sample things, right? These are all functions of sample values. So we want to know the distribution of those things, and that is known as a sampling distribution. Now what they have said is that the sample mean, right? So if we collect, so sample mean is a random variable, right? So sample mean is normally distributed with mean mu and sigma and variance sigma square by n. So whatever this is, this follows a normal distribution with mean mu and sigma square by n, right? So always keep in mind that this is indeed a random variable, so it also has a distribution involved with it. Now, what is the purpose of sampling distribution again? So, what is the purpose? To basically answer questions like this, right? What is the probability that the prediction that I am making and the true value of my population parameter, what is the difference between that, and what is the probability that that difference is as small as 0.1? And to kind of again calculate this probability, we know how theta hat is distributed. So, that is where it comes in. This is a few examples. I have not looked at these examples. Okay, it's better if we just look at ma'am's lecture. This is just a sec. I'm just going to I'm just going to discuss this from ma'am's PDF, so that is much better, right? So, these are some things. Okay. This is something that I wanted to say. So, there are when we look at this sample statistics, right, or just statistics, we very frequently come across these distributions. So, what are these? These are just distributions, right? Just like normal is a distribution, binomial is a distribution, these are also just distributions. And chi-square, it is generally denoted by as this. So, this is the chi-square letter, and this chi-square, this square doesn't really mean anything. So, it is not something squared, it is just how it is written. And the reason why there is a square here is basically this is a positive thing. So, chi-square is never negative. So, if I say ki something, let's say S follows chi-square distribution, then S is never negative, S is positive. So, if you look at the PDF of chi-square, it looks something like this. This is 0 and this is that. So, it is not symmetric, it is asymmetric, and it is like that. So, it is again a distribution. It has a PDF, it has everything, it has mean, variance, stuff like that. F distribution is similar, and the thing is, if you, let's say, if I have a variable z which is normal, and if I have a variable let's say s which is chi-square, then the difference, the ratio of these two things will follow a t distribution, right? So, when we say ki why, if the sigma square is unknown, then the statistics follow a t distribution. Why do we say that? Well, because what do we have? We have x bar minus mu by s by root n, right? So, this is what we have when I don't know my sigma. So, generally we work with this, right? So, generally we work with this, right, where when sigma is known. Now, we know that x bar is normally distributed from the central limit theorem and everything. So, we know that x bar is normal distributed with mean mu and sigma square this, variance this. So, x minus mu is basically normally distributed with mean 0 and variance sigma square by root n, and this entire thing. So, the thing that is in numerator, that is normally distributed. If I know what the denominator is, then this entire thing is normally distributed with mean 0 and sigma square 1. But if I don't know what this denominator is, right, if I don't know what this is and I replace that with my sample standard deviation, which is s, then and we also know, by the way, this is also one of the theorems or result, ki sample standard deviation is chi-square distributed. So, the sampling distribution of s is chi-squared. So, in that case, whatever this is, this becomes a ratio of normal distributed variable and a chi-square distributed variable, and the resulting thing is t distributed, right? So these are the formulas that kind of we need to keep in mind. So we used to get this kind of question ki if z1 is normally distributed and z2 is chi-square distributed, so what would be the distribution of z1 by z2? If z1 is chi-square distributed, z2 is chi-square distributed, then what would be the distribution of z1 by z2, which is going to be f. So f is the ratio of two chi-square distributions. So these things are kind of important, and these things are kind of generally needed in hypothesis testing and to make the confidence interval. But apparently that is not in our syllabus. I don't know why, but it's not. So, and this is a very celebrated result that the MLE of mean, which is x bar, and the sigma hat, whatever this is, these two things are again random variables, right? So sample standard deviation and sample mean, they are again random variables. The thing is that they are independent of each other, right? And this is not trivial. This is, I mean, like we can see, right, कि standard deviation में x bar है. So our first guess would be to say that they are not independent of each other, but they are independent of each other. And again, so x bar follows normal distribution and whatever this is. So we don't actually know the distribution of sigma square or s square, or that is sample distribution. We don't know this distribution. We know the distribution of this thing. If I take all of these things and if I divide that with my sigma square, then it follows a chi-square distribution. Okay, so I know the distribution of this thing, not my sample standard deviation. Although I was saying, but that is for the sake of simplicity. It is actually this that we know the distribution of, and we can kind of manipulate this expression to get some different results. For instance, this one. So this basically says that if you have a normally, so z is normally distributed and y is chi-square distributed, and it is divided by its own degrees of freedom. So if you kind of replace z by any variable that is normally distributed, y with any variable that is chi-square distributed, and if you do this, resulting thing will be t distributed. That is what this says. Similarly, this entire thing, so, and this is basically an application of this, right? So if in this place, if I put z equals to, let's say, x bar by mu, which we know to be normally distributed, right? And if we divide that by sigma by root n, then this entire thing is normally distributed with this, right? So I got my numerator. Now let's do for the denominator. I know that whatever this is chi-square distributed. So let's put that in the denominator. So we'll get summation of xi minus x bar by sigma square So this is my chi-square distributed. Now if I want to put this into this formula, what else do I need? I kind of need this y by v in the denominator, right? So also I don't know this sigma square, right? So what I can do is basically do this little trick. So this I have root n by sigma here, and if I like multiply 1 by n times 1 by n, so this becomes my s square, right? This becomes my sample standard deviation times n by sigma square. Okay, I already have that root n here. What else do I need? This sigma. Okay. Oh, sorry. Just a sec. So let me do it afresh. So if we, instead of z, we put x bar minus mu by sigma by root n, and this is I need square root of something which is chi-square distributed, right? So what is chi-square distributed? This summation of xi minus mu. Now, by the way, 12 baj gaya hai. It's getting late anyway. So I guess we'll just discuss this and leave it here, because I don't think we should elongate this anymore. So I'll just work this out and then we'll stop. So I need something which is chi-square distributed. Now what is chi-square distributed? This thing right here. So basically what I'm trying to say is ki if in this formula instead of z you put x bar minus mu by sigma by root n, and instead of square root of y by v, if you put this thing, if you put this thing, and then you simplify the result. So basically what you can do, you can multiply by 1 by n times 1 by n you can do. So you will basically have s square is your sample standard deviation, times n by sigma square. This follows chi-square n minus 1. If you put this into this denominator and kind of you work everything out, which for some reason I am not able to do right now, I am drawing a blank. If you do that, you will end up with this expression. Okay, you will end up with this expression, and somewhere along the way the sigma squares will cancel out. So that is going to happen. I mean, I guess because you have, let's say, 1 divided by sigma here, and you also had a sigma here in the denominator, right? You also had a sigma here in the denominator, but that is going to come out of the root, and it is going to be sigma, and they are going to cancel out. So the point that I am trying to make is that whatever this is, right, this we already knew that this followed a t distribution. I guess all of us have done hypothesis testing in undergrad or sometime or the other, and we have done this. We used to calculate this, and this used to follow a t distribution. Why does it follow a t distribution? Well, because of this particular thing, of this particular result that we have. If we divide a normal, standard normal variable with a chi-square variable, we get this. So this is it, and we have something else with this. After doing this, we just need to kind of focus on calculating the confidence interval. That is something that we are going to do tomorrow. I need to take a look at this, good hard look at this, because other than that I'll just ramble on, and it won't be of no use. So that was it. Any doubts you guys have? I mean, I know that chapter 8 part was thoda sa sketchy because I khud nahi kiya am. So